On a summer day, walking around Lake Mendota, you might expect to see clear blue water, but often it's transformed into a thick layer of algae. This transformation is driven by excess phosphorus. Phosphorus is an essential nutrient for crops and is applied to agricultural fields through fertilizer and manure. But when crops don't use all of it, it doesn't just stay in the soil. It can be carried away and run off from rain and snowmelt. Once it reaches lakes, rivers, and streams, it fuels the growth of algae blooms, which degrade water quality and harm aquatic life. This problem is especially prevalent in Wisconsin due to the large amount of animal agriculture and manure spreading. To address this, states have developed phosphorus indices that estimate the risk of phosphorus leaving a field. Wisconsin has one of the most advanced indices, called the WPI, which doesn't just rank risk low, medium, or high. It actually quantifies the amount of phosphorus. This makes it a really great tool that is used by agriculture and conservation stakeholders across the state to explore how different management practices impact water quality. For example, a farmer can test how switching from continuous to rotational grazing will impact phosphorus transport in the future. While we see the negative impacts in the spring and summer, actually a lot of phosphorus movement happens in the winter. Rain on snow and large snowmelt events cause large volumes of water to be available, and when soils are frozen, they take in less water, leading to more runoff. These winter processes are really complex to model and make getting accurate estimates of runoff difficult. My research evaluates how well the WPI can predict winter runoff from a field and finds areas for improvements. This prediction works by using information about a field, such as crops, soil, tillage, topography, to estimate the proportion of rain and snowmelt that will contribute to runoff. A lot of my work looked at how the WPI determines rain and snowmelt, and I updated these equations to better account for previously missed events and better represent frozen soils. So these predictions were compared to measured data, and overall I found that the WPI tends to underpredict winter runoff, especially during winters with really high measured runoff. It also performed better on fields with fall tillage. However, my improvements did help reduce some of this underprediction, lowering negative bias by over 30%. So continuing to evaluate the WPI across a range of cropping systems and soils is essential to ensure that users have reliable estimates across the state. Improving winter runoff makes the WPI a stronger tool, allowing for more informed decisions and healthier water bodies.